Hey friends, welcome back to the bread and butter of the squeeze theorem, okay, which immediately begs the question, what is the squeeze theorem and why do we have to use it? Okay. So first, let's talk about what if we didn't know we were supposed to do the squeeze theorem? What if we just had this, find the limit, and we wanted to try it using the things we already know? Well, I see a product. Can I split this up and say the limit of x squared as x approaches 0. Well, this one is continuous. I can just plug in 0. I get 0. Very straightforward. And I can try to do this. Take the limit of sine of 1 over x as x approaches 0. And the deal is, if this limit also exists, remember, then we can say the individual limits exist. The limit of the product is just the two limits multiplied together, right? That would be a thing. So now I'm super interested in finding that limit. Now, furthermore, I look at this and say, well, we've discussed cases where we have an inside function and an outside function. Can we split this up and do the limit of the inside first? And the answer is no. How come? Because if I look at the inside function, the y equals 1 over x, it kind of looks like this. A little bit sloppy on my part, but this is y equals 1 over x. And as x approaches 0, notice on both sides, I'm going up to positive infinity, or over here down to negative infinity. So the limit of this inside function as x approaches 0 does not exist. Well, does that immediately mean this whole thing is broken, the limit doesn't exist? Well, we already saw an example where it was possible to break one of the conditions and still get a limit. Okay, so when all else fails, we try to analyze this function, maybe by graphing it to see if we can gain some intuition. So we go, all right, y equals. I already have sine of 1 over x in there. And this time I'm going to window it so the x's are really close to 0. And I've deliberately chosen y to be between -2 and +2 for reasons. So I hit the graph. And seems legit, and crazy stuff starts happening. And really, this visual output does not do the function justice. This calculator cannot handle what's going on as x gets close to 0, so you just sort of start seeing these gaps in the graph. Well, if we think about the nature of sine, well, what even is sine? So sine is the y-coordinate in the unit circle, right? So if I quickly grab this and draw a circle around here, okay? So if the inside here, this we can call the angle theta, right? As x approaches 0, the angle theta is going to go up toward positive infinity or down toward negative infinity. So what happens in this unit circle if, right, theta starts getting really, really big? Well, the y-coordinate of the graph corresponding to sine will go up to +1, then down to -1, then up to +1, down to -1, and then oscillate between +1 and -1 more and more quickly as this angle goes super big, which is kind of what you're seeing in this graph right here. The graph is oscillating sort of as fast as my calculator can show, but it doesn't approach a single number. In fact, we often will sort of phrase this as this sine of 1 over x approaches all the numbers between -1 and +1, which means it doesn't approach any single number. So this limit does not exist, which means this entire discussion unfortunately leads nowhere. We can't get an answer out of this, so we have to do something new. And that's where the squeeze theorem comes into play. So this is a statement of the squeeze theorem. We are going to ultimately be interested in the function f. But we're saying, let's imagine there are two functions, g and h, so that g is always less than or equal to f, and h is always greater than or equal to f, as long as x is in some interval containing a value a. Right? So imagine we have an interval like from -1 to +5, for example. If g of x is always less than or equal to f, and h of x is always greater than or equal to f, with the exception at exactly x equals a, because we might not have a value there, but it's still going to be okay, as long as this is true for all x in the rest of the interval, okay? And if the limits of these outer two functions, as x approaches a, are equal to each other, and the limit exists, then the argument is that the limit of that middle function has to end up the same value as the limits of these outer two functions, which perhaps, makes a lot of intuitive sense. Because if we imagine, so this is like the picture that you'll always see drawn, that h of x is some function up here. This is like y equals h of x. And g of x is some function down here. Let's do this. This is y equals g of x. And let's imagine f of x is some crazy wacky function that, maybe does this, and then touches that, but then does something in here, and then comes out here and does this. Okay? So the argument is, on some interval, that g of x on the bottom is always less than or equal to f of x in the middle. This is y equals f of x. And h of x on the top is always greater than or equal to f of x. And specifically at this value a, let's just imagine that f of a isn't a value. So f of a doesn't exist. And furthermore, let's imagine, kind of like in the previous problem, the limit of f of x as x approaches a isn't something you can obviously find. What you want to do is you want to come up with a g of x and an h of x that make sure are always above and below, but specifically as x approaches a, the upper function and lower function end up hitting the same limit. So the squeeze theorem states that since f of x is always between those two functions, it gets squeezed to whatever value these two limits approach, right? So the argument is this y value right there is the limit L. And I'm not going to go through a proof for this. The proof itself is actually not super complicated. If you want to look it up, it's pretty cool. And for the most part, right, this is one of those things that feels intuitively obvious and then ends up being true. So we're very thankful for that. So coming back to this original problem, our goal to use the squeeze theorem is going to be to come up with two functions, g of x and h of x, so that this thing is going to be between those two functions, and then we're going to apply the squeeze theorem. Okay. Now, the way we're going to go about this is we're going to make an argument that sine of 1 over x does all kinds of crazy interesting stuff near x equals 0. But what we do know is because of the definition of sine, which is the vertical coordinate in the unit circle goes down the lowest it possibly can at -1 and the highest it possibly can at +1, right? Which is why in this graph I said I chose -2 and +2 as the y bounds for a reason, because -1 is the lowest value we can ever get for the y's, and +1 is the biggest value we can ever get for the y's. So what I'm going to do here is I'm going to write consider the following statement. -1 less than or equal sine of 1 over x, which is less than or equal to +1. Now, this we know is a true statement. Now, the next thing I'm going to say is, all right, x squared, all right, as a number, if I multiply boom, boom, and boom, those three things by x squared, I should be able to preserve those inequalities. So I should be able to say -1 times x squared then is less than or equal to x squared times sine of 1 over x, and this is less than or equal to 1 times x squared, like that. Now we're getting closer to the thing we're interested in, because here this is that. We could call this f of x. We could call this g of x. And we could call this h of x, right? So we've done the first part where we came up with two functions, g of x and h of x, so that this is always less than or equal to the f of x, and this is always greater than or equal to the f of x. Then we want to figure out if those two limits, those, are going to come out to the same number. Let's try this. So we often show our work like this. We write the limit as x approaches, and we're interested in x approaching 0. So we're going to do this is less than or equal to the limit as x approaches 0, x squared times sine of 1 over x, which is less than or equal to the limit as x approaches 0 of x squared. Now, can we evaluate this and this? And the answer is yes, because those two are both continuous functions, which means we're able to just say, 0 is less than this, is less than or equal to 0. So this is the equivalent of us arguing that the limit of the two outer functions both equal the same number L. Well, the only number that can be greater than or equal 0, but also less than or equal 0, is the number 0, which is the conclusion here that the limit of the inside function has to match the limits of the outside function. So we would say, therefore, boop, 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 by the squeeze theorem, the limit as x approaches 0 of x squared times sine of 1 over x is equal 0. Proof complete. That is how we have to approach a problem like this. So this right here isn't so much a homework or a quiz or a test problem as much as it is the most iconic example of using the squeeze theorem to prove a result that we're going to use later. And at the risk of being redundant, I'm going to show you a proof of this because I want to point out something very specific in the proof that partially answers the question in the future, why do we like to do calculus in radians? Okay. So let's pretend that I've already done analysis and I figured out that the only way I can do this limit with the knowledge I have is to use the squeeze theorem, right? Nothing else I know works. So in order to do the squeeze theorem or to apply the squeeze theorem, I have to come up with the lower and upper functions. So the way I'm going to do this is by using some clever geometry. So I am going to draw the first quadrant of a unit circle. Okay. So in this context, we have a unit circle, so my radius is 1. And I'm going to have some angle theta right here. That doesn't look like a theta the way I've zoomed out. There we go. And I'm going to draw a triangle from that point to the point 1, 0. Okay, not a right angle up here, but I can drop an altitude and have a right angle right there. So the area of this triangle is 1/2 times the base times the height. The base is 1, and the height right here is the y coordinate of that point, also known as sine of theta. Okay. Then over here, I'm going to draw this arc from there to there, and I'm going to think about the area of this sector, this pizza slice. All right. So the area right here, it is, if we're in radians, 1/2 r squared theta is the formula that it simplifies to. But let's pretend we don't remember that. Okay. I'm going to take this pizza slice to be a fraction of the full area of the circle. So the full area of the circle is pi r squared, which is pi times 1 squared. And what fraction do I have? I have that much angle out of the full angle at the middle of the circle. So it's theta out of 2 pi radians. So that means theta right here is in radians. We could have chosen to do this in degrees and put 360 degrees down here, but for reasons, as in this drastically simplifies what we have to write down, we choose radians. Radians are amazing, okay? Radians. So those cancel, and I end up with 1/2 times theta. All right. Now, I'm going to extend this segment so that I can drop a line straight down, get a perpendicular angle right there, and I want to know the area of this triangle. Well, 1/2 times the base, which is 1, multiplied by the height here, which I am going to claim is tangent of theta. Wait, how come? Well, I have an idea. Okay, so in this context, theta is a number between 0 and pi over 2, so I'm guaranteed to have a right triangle out here, which means I can say tangent of theta is equal to opposite over adjacent in a right triangle. So the opposite is going to be this vertical height, and the adjacent is going to be this right here, right? Because I'm looking from this angle's perspective, opposite over adjacent. Well, adjacent is just 1, so when I multiply 1 over, the opposite is equal to the tangent, hence this height is tangent theta. Cool? Convinced? All right. Now, as long as theta is positive and acute, okay, so we're in the first quadrant, perhaps you will believe me that this smaller triangle I drew inside the circle is less than or equal to the area of the sector, the pizza slice, and that is less than or equal to the area of the bigger triangle. So I should be able to write 1/2 sine theta is less than or equal 1/2 theta, which is less than or equal 1/2 tangent of theta. And this tangent of theta I can actually rewrite as sine theta over cosine theta because I have a little bit of foresight. Okay? Now, because of this condition, I know that sine of theta is a positive number. It is not 0, which means I can divide all three pieces of this inequality by sine of theta and preserve the inequalities. So I'm going to divide by sine of theta. I'm going to get 1/2 is less than or equal to 1/2 theta over sine of theta, which is less than or equal to 1/2 times 1 over cosine of theta. Now that I can multiply through by 2 and just cancel all the 1/2s. And furthermore, I can take these and reciprocate both sides. So as in, I'm going to take this 1, reciprocate, and make a 1, because 1 over 1 is 1. I'm going to take this and reciprocate and get sine theta over theta. When you do that with an inequality, you end up with the opposite direction inequality. Same thing here. If I take the reciprocal of 1 over cosine theta, I just get cosine theta. Okay? Now, this is the same thing as that. And so I'm looking at this and thinking to myself, I can set up a squeeze theorem case where I have a lower and an upper function. However, I had to make the restriction that theta is positive here. And I am approaching, right, 0 from both directions, and that x is going to represent the same thing as theta. So I have to have a way to establish another inequality for negative values of theta. So, not a big deal. I'm just going to draw the fourth quadrant of the unit circle. So once again, the radius is 1. And this time my theta is a negative value. All right. So I'm going to draw this arrow to indicate theta is going clockwise. It is a negative number. But by the same logic, I can say the area of this triangle is 1/2 times the base times what is the height this time? The height physically is a positive number. The y-coordinate of this point is a negative number. So the height should just be the negative of the y-coordinate. The negative of the y-coordinate, because sine of theta is a negative number. Negative of negative gives me the positive height. Okay, so we're good. Then I go over here and say, I want my sector area, and this area out here is going to be pi times r squared times how much angle I have out of the full circle. But since theta is a negative value, in order for me to preserve a positive area, I have to go negative theta over 2 pi. And I really apologize, I didn't have the foresight to make that show up clear. Okay, so this is pi r squared times, that is now a positive number because theta itself is negative. All right, so now this comes out to negative theta over 2. But once again, we are in radians. Beautiful. Similar logic. Severely regretting the way I drew this picture. Hopefully you'll forgive me. So the area of the bigger triangle is 1/2 times 1 times the vertical here is not positive tangent theta, because we know in the fourth quadrant, tangent of theta is negative, because sine of theta is negative, but cosine of theta stays the same. So the way we make the height a positive value is we just go negative tangent theta here. Okay, so now for theta that is between 0 and negative pi over 2, so if theta is a negative value, we know that small area, so this is 1/2 times negative sine of theta, is less than or equal to negative theta over 2, negative 1/2 theta, which is less than or equal to negative 1/2, sorry, my face is in the way, tangent of theta, which once again I can write as sine of theta over cosine of theta. Okay. So it's very similar to this, except now we have negatives. So I can divide by sine theta like I did before, but here's the thing. When I divide by sine of theta, okay, sine of theta is a negative value because theta is a negative value. So when I divide by sine theta, I'm actually dividing by a negative number, which means I have to flip these inequalities. And then when I multiply by -2 to get rid of the negative 1/2, I'm multiplying by a negative number again. So I will have this situation. Which is the same thing I had back here. When I reciprocate, I end up with 1 greater than or equal to sine theta over theta, which is greater than or equal to cosine of theta. And I have the exact same set of inequalities, except now I've established it for positive theta and negative theta. So after all that talking and scribbling, we're back to this limit that we're trying to find. And the argument is we want to consider the following inequality, that cosine of x is less than or equal to sine of x over x, which is less than or equal to 1. Where did I get this from? I got it from all this talking and scribbling. Cosine of theta is on the lower end, 1 is on the upper end, and sine of theta over theta is in the middle. And this works for all theta that's between 0 and pi over 2, and then between negative pi over 2 and 0. So I can say, and this is for all x in except at x equals 0. Right? So in the squeeze theorem, we needed for all x in an interval containing a, which is going to be 0, except possibly at x equals 0. We're good. We're ready to use the squeeze theorem. So how do we do this? We write the limit as x approaches 0 of cosine of x is less than or equal to the limit as x approaches 0 of sine of x over x, which is less than or equal to the limit as x approaches 0 of 1. That is a continuous function. Never actually proved that to you, but kind of like with sine, trust me, bro. So I can just plug 0 in to cosine of x, and I get 1. And then over here, This is just a constant. It's always 1. So if I take the limit as x approaches 0, I get 1. And therefore, this matches this. And by the squeeze theorem, the limit of sine of x over x as x approaches 0 is equal 1. And this is a very, very important result for the future. And just for funsies, right, since I have my calculator pulled up, I'm going to go ahead and show you the graph. Cosine of x, 1, and sine of x over x. So I have these three things. So the order I'm going to graph them, first of all, is cosine of x. And after that is going to show up as 1, a flat horizontal line. And then we're going to have sine of x over x. And it's important to note, in the window, so I have negative 10 as the far left x and positive 10 as the far right x. So notice that this middle black line, sine of x over x, isn't always between the blue and the red graphs. But that's okay, because I only need it to work for an interval that I get to pick, an interval that contains the x equals 0. So my interval is from negative pi over 2 to positive pi over 2. Pi over 2 is like 1.57-ish. So it's from about there to about, in fact, I can just change my window, right? I can say this is negative 1.5 to positive 1.5 and hit the graph. And while this is graphing, I'll keep talking. But what we're trying to show is that those two graphs end up below and above sine of x over x. And since those two approach the same limit, the y value of 1, that the thing in between has to get squeezed between the bottom and top graphs. So the only thing it could possibly be as a limit is 1. So at the end of today's discussion, we have two super important consequences of the squeeze theorem. This result, which I proved to you, and this result, which I did not prove to you, but it's just a few steps of algebra from this one, and I don't think there's much value to add to the discussion by showing that proof, so I'm not going to. Important thing to reiterate. When we did this, we put the angle in radians, which means anytime you see this result or this result, x is in radians. Okay, x is in radians. And these two results will come back. We're going to use these to prove the derivatives of sine and cosine in a future unit. So that's part of the reason we emphasize the squeeze theorem at this stage, not just because it's cool, because it is cool, but because these two results are necessary for the future. Okay, and quick corollaries of these, I'm able to take the reciprocal here, using sort of division property of limits. So if I take the reciprocal here, I end up with the reciprocal of 1. That is totally valid. But if I try to do it here, I get does not exist. So if I take the limit as x approaches 0 of x over 1 minus cosine x, I end up with a does not exist case. And I can also do a composite function kind of situation, where if I take the limit as x approaches 0 of, let's just say, like sine of 4x over 4x. So if this matches that, then I end up with 1. And ditto here, if I take the limit as x approaches 0 and I have something 1 minus cosine of, let's go with 3x all over 3x, as long as this 3x and this 3x match, then I'm able to conclude this is equal to 0. And perhaps that will come in handy when you're doing some problems. Okay, so sometimes it's a little bit hard to appreciate what the squeeze theorem does for us at this stage, but I super promise these two results are important for the future. We had to get them, which means we had to address the squeeze theorem in order to get these results. All right, well, hopefully some of that was fun, and I'll see you all next time. Peace.